In today's lecture, we're going to look at certain limits that involve infinity. So this can occur in two different ways. Either the independent variable can approach infinity or possibly negative infinity, or the dependent variable can approach infinity or negative infinity as the independent variable approaches a finite point. So let's start with just taking a look at the first case. So the independent variable x might approach infinity. So here's the x-axis. So I'm going to draw, some graph that does anything, and then after a while it just kind of levels off. So it's supposed to approach some sort of horizontal line. So it would look a little bit like this. In fact, let's make it not veer away. So this is supposed to get closer and closer to this horizontal line, like that. So as x gets larger and larger, the outputs of the function f of x are getting closer and closer to this line y is equal to L. So we have this horizontal line, and the outputs of the function f of x become closer and closer and closer. So it can do whatever it wants for as long as it wants, but there's some point that it will always be, this close to L, somewhere within that distance. And then at some point, it will always be within this distance, and at some point, it will always be in a smaller distance, and so forth and so forth. So basically, the outputs are leveling off at some ultimate value. So in this case, we say that the limit as x approaches infinity of f of x is equal to L. And this is called the limit as x approaches infinity of f of x is equal to L. Right, so the outputs are becoming closer and closer to L the larger the inputs become, in value. So if you're at x is equal to 1 googol, there's a pretty good chance that f of 1 googol is very, very close to L. Of course, f of 1 googol could really be anything it wants, because this really means that it's really just in the limit as x goes to infinity. So maybe it hasn't settled down over the first 1 googol x units, but it will eventually. So that's kind of unfathomable because 1 googol is such an enormously large number. But it is possible for the limit to still have a value L, even if it takes a long, long time for it to get there. The defining characteristic here is there is some x value. It could be very, very large, such that the f of x will be very close to L for all points after that. So if there is such a number L, we say that the limit converges. So if there is such a number L, we say the limit converges. So converges is an important word that we'll use throughout calculus, Calc 1 a little bit, Calc 2. It basically means that the limit exists. So the outputs of the function converge on L, right? So there's some number that the outputs will converge to. Otherwise, so in other words, if we cannot find any number that satisfies this, otherwise the limit diverges. So diverges basically means the limit does not exist. Most of the times you can say the limit's equal to infinity, but that might not be the case. So there's different ways in which this limit might not exist. So one example is if you just have f of x is equal to x. So as x becomes larger, the output also becomes larger. X of 1 million is 1 million. X of 2 million is 2 million. Right? The outputs never settle down at a fixed value because we just have a line that's continuing to increase forever and ever without ever settling down at a particular output. So that limit diverges. So we can say the limit as x goes to infinity of x, we can actually say that's equal to infinity. Or we can say it does not exist because technically the limit does not exist. So the limit diverges. So this is an example of a divergent limit. And it's divergent because it doesn't settle down to a particular number. So the outputs don't approach some particular long run output. Another example where a limit might diverge is just with the sine function. So you'll recall the sine function, I'll draw it on the same graph, looks like this. Well, this doesn't go to infinity, it doesn't go to minus infinity, but it oscillates back and forth. So there's no y value that it settles to. You know, it's not settling to 0 because no matter how far out you are on the x-axis, there's always going to be a point after that where it's going to be equal to 1. The output will equal 1, and then after that the output will be minus 1, and then plus 1, and then minus. So it's not settling at any particular output value. It's going up, it's going down, it's going up, it's going down. It never settles. It keeps oscillating up and down. So that's another example. So we can say the limit as x goes to infinity of sine of x does not exist. It's oscillating up and down without leveling out, right? So if we said, what's the limit as x goes to infinity of sine of x over x, this is going to equal 0. Because sine of x is bounded between minus 1 and 1, so you have something that's oscillating times 1 over x, and 1 over x becomes smaller and smaller and smaller and smaller. So you have some oscillations that damp out and become smaller and smaller, and so the y values are just going to approach 0. So that is the limit of sine of x over x. So we saw this generic definition for the first graph I had. So the limit as x goes to infinity of f of x is equal to L. It just means that the values of the function level out at the value L. Now, when this is the case, we call the line at which they level out to, this orange line right here, that's called a horizontal asymptote. Horizontal asymptote. So let's do a definition of that. Definition. So a line y is equal to L is a horizontal asymptote of the function f of x, of the function f, if the following holds. If the limit as x goes to infinity of f of x is equal to L, or if the limit as x goes to minus infinity of f of x is equal to L. So you get either or. So you can have up to 2 horizontal asymptotes. So let me show you why that, an example of that. So here we have our axes, x-axis, y-axis, and let me draw the 2 asymptotes. So there's one asymptote, let's draw another one down here. And now let's add a function that has these 2, so maybe this is y, maybe this is y is equal to 2, this is y is equal to minus 2. So our function might do any weird thing here, but eventually it will level out at an output of 2. And then conversely, if you go to large negative values, eventually it's going to level out at minus 2. So basically, the 2 asymptotes up to 2 occur at when you basically take the limits as x goes to plus infinity or as x goes to minus infinity. So we have one limit as x goes to plus infinity and one limit as x goes to minus infinity. So those are our two asymptotes for this function. And so you can always find the asymptotes by taking those limits. So for example, let's take a look at f of x is equal to 3x to the fourth plus 9x cubed plus 27x squared plus 13x plus pi divided by 7x to the fourth plus 18x squared, x cubed, why not, plus 7x plus 9. So our question is, what are the, or where are the horizontal asymptotes, if there are any? So we need to take the limit as x goes to infinity of this function. Now whenever you're taking the limit as x goes to infinity of a ratio of polynomials, you want to look for the leading coefficients. So the leading coefficients are the coefficients of the highest power. So the highest power here is x to the 4, and in the denominator it's also x to the 4. So the two powers are balanced, which is good, which means that they'll both kind of go to infinity at the same rate. If we had an x to the 4th in the numerator and an x to the 5th in the denominator, in that case the denominator is getting larger faster than the numerator. Because the whole idea is the larger the power of x, the faster it's going to get to infinity. X to the 4th goes way faster than x cubed, which goes faster than x squared, which goes faster than x. Right? Think about 1 million to the 4th power. That's an awfully big number. It's a million times bigger than 1 million to the 3rd power. 1 billion to the 4th power is 1 billion times bigger than 1 billion to the 3rd. So if you're thinking about, well, what would this look like if x was really, really astronomically large? Well, if you don't have your glasses on and you're looking at this 3x to the 4th is the dominant term in the numerator. It's way bigger than all of the other terms, and the more so that's true, the more so that x is large. And similarly, in the denominator, 7x to the 4th way surpasses everything else in the denominator. So when we take the limit, x goes to infinity, 3x to the 4 plus 9x cubed plus 27x squared plus 13x plus pi over 7x to the 4 plus 18x cubed plus 7x plus 9. The deal is we want to look for the leading coefficients, 3 and 7. First, we check that there's a balance of power, 4, 4. The largest power in both is equal, and so we look at the leading coefficients, and the limit is simply going to equal the ratio of the leading coefficients, 3 over 7. It's that easy. And the reason is that 3x to the 4th is the dominant term in the numerator, the 7x to the 4th is the dominant term in the denominator. So as x gets larger and larger, this ratio will approach 3 over 7. As x goes to minus infinity, the same thing happens. Right? So it's going to be the same. So basically we have a horizontal asymptote, y is equal to 3 over 7, like that. Exponential functions win out over any polynomial. So even if you're looking at, for example, limit as x goes to infinity of x to the 9999 plus 3e to the 0.01x over 12x to the 9999 plus e to the 0.01x, what would you do with this? Well, x to the 9999 seems very large. And if you plug in to, let's say you graph it, that might be the dominant behavior for small values of x, because the e to the exponential term doesn't grow very quickly at the beginning because there's a very small growth rate. But exponential functions always win out over any degree polynomial. As we'll see at the end of Calculus 2, an exponential function is really like a polynomial of infinite degree. So it's going to win out over a polynomial of degree when Google, like x to the power when Google plus x to the whatever plus x to the whatever and so forth. Wins out over every polynomial. So here we have exponentials, and it's a positive up here. So remember that indicates exponential growth. But these two exponentially growing terms balance, right? This one balances with that. So this limit's going to be the ratio of 3 to 1. So the limit's equal to 3. Now this one's interesting because of what happens at minus infinity. So at minus infinity, let's take a look. What's the limit as x goes to minus infinity of x to the 9999 plus 3e to the 0.01x over 12x to the 9999 plus e to the 0.01x. So you might say, well, it should be the same thing, right? It's just 3 over 1. Wrong. So as x goes to minus infinity, we have a different story. So we have kind of a different picture. So to understand this, let's take a look at just the graph of an exponential function. So an exponential function e to the x looks like this, right? E to the x. Or as long as you have a positive growth factor in the exponent, e to the 0.01 will look like that as well. So as x goes to infinity, we get exponential growth. But here on this side, we get decay to 0. So as x goes to minus, because if you think about it, e to the 0.01x, if x is negative, it looks like e to the minus 0.01 absolute value of x. Right? If x is less than 0, it looks like that. So it's like a negative in there, which comes from the x itself. So that's going to be the reciprocal of e to the 0.01x. So this output is the reciprocal of this one right here. So e to the minus 3 is the reciprocal of e to the 3 and so forth. They're inverses of each other. So if this one is large with positive x, it has to be super small with negative x. So in this case, as x goes to minus infinity, these terms are getting small and small and small because you have a negative in the exponent. So it's these terms that are dominating. And x to the 9999 is going to be a very large negative number. X to the 9999 in the denominator is also a very large negative number. So since they're both negative, the numerator and denominator, it's going to be a positive. So this limit is equal to 1 over 12. So you see with this function, we have two vertical asymptotes, one at y is equal, or horizontal asymptotes, one at y is equal to 3, the other one at y is equal to 1 over 12. Now we do the same sort of deal with vertical asymptotes. So let's draw our graph. So suppose we have something like this. That's not exactly vertical, it's not intended to be. Because functions cannot, they have to satisfy the vertical line test. So even though I kind of drew this imperfectly, it's supposed to, the idea is that, it just kind of approaches that. So it just kind of goes and approaches that vertical. So as you move to the right, smaller and smaller amounts, you're going up more and more. So it's basically like if you turn your head sideways, you would get a horizontal asymptote, but it's not sideways, so it's a vertical asymptote. So let's say this is at the point A. So the line x equals A, which is a vertical line because it represents every point in space that has the every point xy is such that x is equal to a. So it's a set of the points a comma y for every y value. That gives you a vertical line. The line x is equal to a is a vertical asymptote of the function f if the limit as x goes to a from the left of f of x is equal to plus or minus infinity, or the limit as x goes to a from the right of f of x is plus or minus infinity. So like that. So basically, it's a finite x value, but the y value is approaching either plus infinity or negative infinity as you're approaching that one x value from either the left or the right. So an example of that would be just f of x equals 1 over x. So 1 over x looks like the following. So 1 over x looks like this. We go up like that. No. Actually, we go down like this. Looks something like that. Right. So the line x is equal to 0 is a vertical asymptote of f of x equals 1 over x. And we can write the limit as x goes to 0 from the right is infinity, and the limit as x goes to 0 from the left is minus infinity. Right? Because as the x value is approaching 0 from the right, so using values of x that are greater than 0, the y value is getting larger and larger. So in other words, as x goes to 0 from this way along the graph, the y values are going up and up and up to infinity. Right? So x never gets to 0 and y never gets to infinity, but it gets higher and higher arbitrarily as x just approaches that one point. Similarly, as x goes to 0 from the left, right, we're only considering values less than 0. So now we're just considering this behavior, and the values are becoming arbitrarily large negative numbers. So the outputs are approaching negative infinity as x approaches 0 from the left. So this would have a vertical asymptote at x is equal to 0.